Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my great pleasure to welcome Saurabh Chaudhary, who is an assistant professor at Penn State University. So Saurabh graduated in 2007 from UPenn, and he won the ACM SICPLAN Doctoral Dissertation Award. So Saurabh has a wide variety of interests. He works in program verification, parallel programming, logic and automata theory, and today he's going to tell us about parallel programming. So over to you, Saurabh.
Thank you, Sumit. It's a great pleasure to be here. So today I will tell you about this parallel programming language and programming model that I have been working on for almost a year now. So the focus of this model, which is called Chorus, is data parallelism. So in the space of data parallelism, the main success stories have been either when the granularity of parallelism is highly coarse-grained, and an example is map-reduced, or when we are working with dense data structures with highly fine-grained computations. So an example of that is these numeric computations that are common in scientific computing on dense arrays. And in addition, there are some problem-specific methods. For example, people have worked a lot on parallelizing n-body simulation and certain other important problems like that. So here, our goal is not to address just one or two specific applications, but a range of data parallel computations over large unstructured shared memory graphs. And here, the granularity of parallelism is not known in advance. In fact, it's not predictable by static analysis. So in the average case, there is a lot of data parallelism in these problems. But in the worst case, there is no parallelism at all. And as we will see, there are lots and lots of applications which fall into this category. And our goal when we offer this model will be high-level correctness as well as efficiency. So for example, we would aspire to achieve race freedom at the language level, or deadlock freedom. And also, we would like to express the essence of this kind of parallelism so that our compiler and runtime system can take advantage of that. Now, a classic example of an application of this sort is Delaunay mesh refinement. So here, the problem instance is a triangulation of a set of points. So you're given a set of points, and you are building triangles with these points as nodes. Now, what you want to achieve are these two properties. So the first property is known as the Delaunay property, which is that no point is contained within the circumcircle of a triangle. As you see, that's the case here. Okay? But the second property is what's known as the quality property, which is that all the triangles that you get in this mesh, they satisfy a certain goodness constraint, which is that in this case, there is no triangle where there is an angle with that's greater than 120 degrees. So typically, you get meshes when this quality constraint may not be satisfied. So what you want to do is that you want to refine the mesh. You want to add new points to it and retriangulate it so that there are no bad triangles left in the mesh. So this is the problem of Delaunay mesh refinement. Now, let's look at this a little bit more closely. So the one classic algorithm for this problem works as follows, that you collect in a data structure known as a cavity all triangles whose circumcircle contains the new point. So you have added a new point to refine the mesh. And now what you do is that you collect all these triangles, and as you have seen here in the second picture, I have colored them in a different color, and then you retriangulate them, like I've done in the picture on the right. So actually, it so happens that even after you do this thing, some new triangles may again violate this quality constraint, so you have to continue. But there is a guarantee that this algorithm will terminate. So that's that requires some reasoning. So let's look at this algorithm in the form of pseudocode. So I have a mesh, and then I have a work list in which I'm going to collect all these bad triangles. And then I'm going to pick a triangle from this work list. I'm going to create a cavity. I'm going to expand the cavity. And then I'm going to retriangulate it. And finally, I'm going to update the mesh, and I'm going to continue until there is nothing left in the work list. So observation number one, there is no kind of, so these cavities that we have here, these are contiguous regions in the mesh. But the second observation, which is not actually obvious, is that in the worst case, the cavities can encompass the whole mesh. So you can create such an instance. Now, what do we do if we want to parallelize this algorithm? So the first observation is that here we are working on a complex unstructured graph, which is a mesh. And we do not really have properties necessarily that we can use in parallelism. For example, the size of a cavity, as we have noted, can encompass the entire mesh. So what we will do here is that we are going to view this problem more abstractly as a computation over a graph. And in this case, we can view these nodes in this graph as triangles and edges representing adjacency between triangles. And so by the definition, a cavity corresponds to a neighborhood, a contiguous region in this graph. And we are going to use this observation later. But let's continue. So now what's the atomicity property that we want to satisfy? We want these cavities to be retriangulated atomically. And non-overlapping cavities may be processed in parallel. However, this question of what can be done in parallel seems impossible to handle with static analysis. And the reason is that the shape of the data structure, it changes greatly over time. Moreover, it's extremely input dependent. It's easy to create a pathological instance where you are going to get no parallelism at all. And there has been a lot of work on this type of parallelism of late, notably by Keshav Pingali's group at UT Austin. So just to note that this is not just one isolated application. There are lots and lots of similar problems. So in the space of meshing, there is mesh refinement, there is triangulation. There are problems in clustering, ray tracing, maintenance of social networks, graph problems such as spanning tree and flow computation, n-body simulation, sparse problems in scientific computing, sparse matrix vector multiplication, and even some program analysis problems. So I added this for the effect because I primarily work on program analysis, iterative data flow analysis, and Patronet simulation. So this then represents a class of applications which is fairly large, but where these traditional static techniques of extracting parallelism don't really work. So what can we do about it? So what I'm going to do here is that first I'm going to present more abstractly our programming model and show how it can be used to encode that application I showed, Delaunay mesh refinement. And then I'm going to present a more concrete language called Jchorus, which is an embedding of the model on top of the sequential subset of Java. And then I'm going to talk about implementation, and finally I'm going to talk about some ongoing work on embedding this model into Habanero Java, which is an offshoot of IBM's Extend language. Yes?
These kind of applications.
Right.
How well does SIL-style work stealing queue implementations, how do they perform?
So as you will see, our implementation has some stuff related to work stealing queues, so we are using some of the ideas there, but I do not think that alone will suffice. So we are going to come to that, and maybe at the end we can discuss this in more detail. So one of the interesting observations here is that in all these applications, there is a common property of locality, which is that even though you are doing computations that in the worst case can require global access to a gigantic data structure, in the typical scenario, that is not at all so. So for example, we ran some experiments on a mesh of about 100,000 triangles from these benchmarks from Keshav Pingali, and we found that the average size of a cavity is actually only 3.75 triangles. And the maximum cavity size was 12 triangles. So in that case, there is a lot of parallelism in this problem, And the essence of that is perhaps this average case locality. But again, there is no way to know this ahead of time, what is the extent of locality in a particular, for a particular application. So the main idea of Chorus is that since we are working on these local regions in the data structure, why not let these regions be the drivers of the parallel computation, just as objects are the drivers of computation in object-oriented programming, or concurrent objects are the drivers of computation in the actor model. So we are going to make this more clear soon. So let us first phrase the problem a little bit more abstractly. So I'm going to view from now on these problems as a problem of parallel computations on graphs. So here I have a giant graph, and this represents the heap. And the objects here correspond to the nodes. The edges here correspond to the pointers. And I'm going to refer to an induced subgraph in this heap as a region. And so an assembly, in our terminology, is a region in this heap that is equipped with a thread of control. So the typical situation would be that these assemblies would be short-lived and speculative. And we are going to see what this means in the context of some applications. So one point I would like to make here is that this might remind some of you of the actor model of computation. So as we will see later, there are some important differences. But for one here, we have this property that all these regions that are there in the various assemblies in the heap at one time, they all form partitions of the heap. And they are all isolated. Objects in them are completely isolated. Okay? And second is that there is no a priori guarantee on how big a region might be. It might consist of one object. It might consist of the entire heap. Okay? So in a situation like ours, we need to talk about not just static data partitions, but partitions that actually change over time because of the very dynamic, adaptive nature of these applications. So our primitive for synchronization, in fact, this is the only primitive for synchronization here, is merging of assemblies. So here we have assembly I and assembly j, and there is an edge from this I to j. And so I can now merge with j, and the result is this bigger assembly that we see at the bottom. And this assembly j, which previously had ownership of that region, that now dies. So in order to rule out races, we require that j must be in a so-called ready state. That is, it should not be doing in the middle of doing some sort of an imperative update while this merge happens. So again, I'll clarify what that means. So then merging is a way in which we coarsen the granularity of parallelism in the heap. So how do we refine the granularity of parallelism? Well, it's splitting. So here, what we have is that we have assembly I, and I has now split into these assemblies I1 through I6. Okay? And then this tau, okay, so let me actually get to that in a little bit. So for now, let's just get this picture that assembly I has split into these constituent assemblies. Now, one of the things to note here is that this j is completely oblivious to what has gone on inside I here. So I can split, j doesn't have to know. In other words, this splitting operation is not actually a synchronization construct. Whereas in the previous case, for merging, there is actually synchronization involved because we are saying that j must be in a ready state while the merge happens. Okay, and finally, an assembly being having an imperative computation associated with it can actually modify its heap as well as its local variables. So the restriction, though, is that objects inside an assembly are isolated, which means that you are not allowed to follow that pointer, read some data, and do some modification of that. That's not permitted. Everything else is permitted. So, okay, that sounds nice, but what do programs here look like? So what we do here is that we just generalize, we just seek inspiration from object-oriented programming, and we define the notion of an assembly class. And an assembly class consists of a set of local variables, a set of guarded updates. So it's the computations here are in the guarded command style. And there is a constructor which creates an instance of an assembly from an assembly class. And then there are some things called public variables, which I'm going to explain soon. And a program is simply a set of classes. And each assembly, we are going to view it as this sort of a very simple state machine. So each assembly can be in a busy state, which means that it's now executing an update. So remember that we have these guarded updates. So the pattern is that evaluate the guard, execute the update, then come back, and then again do this again and again, right? So this is the state when an assembly is executing an update. And this ready state, which is where the assembly starts, and this is the default state, and it goes back to that after finishing an update, is a state where an assembly can actually be preempted by another assembly. So an assembly can now be merged by a neighboring assembly and die as a result. And when an assembly dies, it just goes to this terminated state. So let's now look at the structure of computations here a little bit more closely. So first of all, these guarded updates are simply of this form, that there is a guard and there is an update. And the rule is that this guard is executed atomically. After that, this update is only going to refer to the objects that are owned by the assembly. Therefore, there is no further need for trying to acquire locks over individual objects. So that's the idea. So again, guard is executed atomically. Update only refers to the objects that are owned by the assembly. So now the construct for merge is going to happen actually within guards. So this is a slight difference from standard guarded command languages, that our guards can actually have these effects of merging two assemblies. However, they cannot modify the heap. So they cannot have effects that are imperative in that sense. They cannot touch the heap. However, they can change the structure of concurrency in the heap. So here at the top, I have this guarded command, merge u.f followed by s. So this says that, try to do this merge. So I, when it executes it, tries to do this merge along u.f. So u is that object at the top. u.f, therefore, is the reference which points outside of I. And it says that try to merge with this. If this merge goes through, in that case, the guard evaluates to true. And in that case, execute the command s on the new region that you acquire as a result. Yes?
Your u and f, are those, should I think of those as two arguments to the merge? That is, you're passing in both the u and the u.f?
No, you should see it as u.f, as in Java, that it's a reference. So u is a.
But in that case, how do you know what you're merging to? What's the capital S?
So S is the statement that you're going to execute after you do that.
So if you're saying that the parameter to merge is, there's just one parameter.
Right.
And it's going to be whatever the F field points to.
Yes.
But how do you know what you're going to join that to?
So you have no control over that, aside from one thing, that I have not shown here. You can specify the type of the assembly that you are going to join with. But aside from that, there is no control about who you will merge with. So,
and in particular, it might not merge with the assembly that contains u.
No, u is what you contain. So u is within I, right? I is trying to execute this. So u.f is the reference that points outside of I.
So I refers to the whole assembly.
Yeah. So sorry, it may look like that's just that one object. No, it's the whole assembly. And then there is a slight refinement of that, which is that you can also guard this with an additional guard, which is g in this case, which just says that g is a constraint that's evaluated on this assembly I again. And when this property g is true, at that point you try to execute this merge. If it goes through, then you execute s. Okay. And as for guards, that's really what we have. So we do not really need anything further. And the split, as for splits, so what we have is that it's just a command that's executed within that s thing that I showed. That there is a guard and there is an update, and that update was that s, that symbol s. So the split is executed within that. And when a split happens, it just produces something like this. And the syntax is like this, that you can do split tau, where tau is the class of the assemblies that are being produced as a result of the split. And this P1 through Pn is going to be the parameters that you pass to the constructors of these new assemblies. And that's the way you pass some local state from this parent assembly to this children assembly. Yes?
Merge operation can fail and split can't fail?
Split cannot fail because it doesn't depend on anybody else, right? It's a completely local operation. Whereas merge is a synchronization construct, and as a result, that might potentially fail. And finally, local updates are, as I said before, so this is just like in Java, except again, if you try to access something that's outside your assembly, then you are going to get an exception. And there are some refinements of that. So one version of merge, for example, is that you can create a new assembly of a new type when you perform the merge. Because remember that previously when I merged with J, it was just I. So now you can also create a new thing in the process. And likewise, you can. There is also a refinement of split, which is that earlier we had to split into all these individual components, assemblies that contained only one object each. However, you can also basically release one of the objects in the assembly and create one assembly out of that. And that would be the split one. But the most interesting constructs are really the ones I showed earlier. OK, so enough about this sort of abstract discussion of the language. Let's look at an application. So here, let's say we try to implement this Delaunay mesh refinement application in this language. So how will we do this? So we will choose two kinds of assembly classes. One will be these triangles, and another will be these cavities. And what does each triangle do? Each triangle determines if it's bad or not. If it is bad, then it merges with a neighboring triangle to form a cavity. Okay? What about a cavity? So a cavity can determine whether it has all the triangles needed to finish the retriangulation, right? And that's a local operation. So if it finds that it needs more, then it tries to merge with a neighbor. If it finds that it has enough, then it's going to just retriangulate locally and then split back into these triangles. Because now you're sort of back into the default state. All these triangles are back. And you're going to continue. This process is going to continue until there is no further activity in this solution, if you will, solution of triangles which are just merging and splitting with each other. So the code then looks kind of like this, that I have one assembly class called triangle. And the action within is that merge with v.f. So let's say v.f corresponds to a neighbor. So you merge with that and become a cavity when this property is bad is true, meaning that you are bad. This triangle is bad. Okay? And that's the only thing that a triangle does. Otherwise, it just stays inactive. What about a cavity? The cavity determines if it's not complete. If it's not complete, then it's going to merge with, again, let's say this points to an arbitrary neighbor, and it's going to form a bigger cavity. And if it's complete, then it's going to retriangulate, and then it's going to split into these individual triangles that form it. So what happens then if there is a conflict? Suppose you're trying to grow a cavity. You're trying to merge with more and more triangles, and in parallel, there is another cavity that's being formed, and these two things collide. What happens then? So remember what we said, that when one assembly merges with another, the assembly that is on the receiving end of the merge dies as a result. So what that means here is that there is one cavity that's being formed, another cavity that's being formed, and then one cavity gets absorbed by another. So what this will lead to is that all the work that one of the cavities did up to this point will have to go, right? In a sense, the computation that you are trying to achieve is rolled back. However, so there are some subtleties here. So in some sense, the work that you set out to do, that will not be finished. You are kind of back at the original state. However, at the end of all this, when the cavity that is the killer, if you will, the cavity that does the absorption, this cavity at some point will have done its job. And then it's going to split again. And then the original thing can start all over again from scratch. OK? Are there questions? Yes?
Every time you merge with other cavity, you can complete the whole work. Is there like cases when you need to merge with two cavities? So you have live log, time log.
So I'm going to address the live log deadlock issue soon. But you cannot merge with two cavities at one time. You are going to merge with one assembly who's going to be your neighbor. But when you do the merge, then the cavity that's on the receiving end of it, that has to go. And as a result, all the work that it has done until this point, that work is basically rendered worthless, right? Because you're not it's not able to finish what it started. However, the point is that eventually this cavity who killed it, killed this other cavity, this cavity will have finished its work. And then it's going to split off again. And then, presumably, if that work still needs to be done, that work will again start from the beginning, and it's going to reach its final point if it's not interrupted by anybody else, and then it's going to do the retriangulation and then split back, and then it'll all be over. So let's now look at some of the other approaches. So I'm going to give a few other applications that we can encode in this style, but let's look at some other competing approaches. So the first question is, of course, what about threads and explicit locking? So here, perhaps the main objection is that the heap in shared memory languages is a completely global entity. And furthermore, you have arbitrary aliasing. And as a result, if you are trying to ensure that there is there are not multiple objects that are trying to multiple cavities that are trying to work on the same object at the same time, that's very hard to do. And it's also low level and error prone. So what about software transactions? So here, what happens is that this burden of reasoning is really passed on to the transaction managers. And in most implementations of software transactions, the conflicts between two activities that are happening in parallel but happen to conflict on some data item, that's detected by monitoring reads and writes to the memory. And as a result, this either leads to you doing some sort of conservative analysis and getting conservative results, or it is very expensive because dynamically you have to really search the entire memory and try to see if there is a conflict or not. So what about static data partitioning, as is there, for example, in languages like X10? So here the problem is the unpredictable nature of the computation. You might have started with a data partition that was very nice, but after a while, because of all these changes, it may become quickly bad. So you need some sort of an adaptive mechanism, and really what our constructs for merge and split offer is a way to implement this adaptive nature of isolation in using a few simple constructs. So finally, what about actors? So the actor model is perhaps the most well-known and the oldest type of data-oriented parallel programming. So if you are going to model this problem of mesh refinement using actors, what you would do is that you would give each actor a set of cavities, right? And then what would expansion mean? It would mean that one actor passes around some triangles to another actor. So now there are two ways of doing this. One is that you would copy the triangles and send it to the other person, but this presumably would be too expensive. But then the other option is to just pass around references, but on the other hand, this introduces problems like aliasing and races. Note, on the other hand, that in our model, there is no aliasing of objects. So as a result of merges and splits, objects get transferred from one entity to another. An entity does not have aliases to objects that are owned by other entities. So that's an important point. So finally, if I'm talking about irregular applications, I have to talk about Galois, which is Keshav-Pingali's system for irregular data parallel applications. So this is, in this system, what they do is that they annotate data structures with information about commutativity, associativity, et cetera, and have iterators that are not just over lists, but also over sets and posets. And this is a very different style of programming. We see ours as an alternative that's trying to address the same problem. OK. So let's now look at a few other applications. So another application that has been looked at a lot in the setting of this sort of parallelism is Boruvka's algorithm for minimum spanning tree. So the parallel version of this is as follows, that you have this graph. And in the beginning, you start with all these small spanning trees, which correspond to just one or a few nodes each. And then these small spanning trees merge to form bigger and bigger spanning trees until finally you're going to get this spanning tree that covers the entire graph. So this is pretty obvious how to model this in our language. So what you do is simply you model these spanning trees as assemblies, and merging is just a direct construct in this system. Another application from Pingali's benchmarks is that of focused communities. So the goal here is that you have a giant social network where there are updates being made continuously. And what you want to do is that you want to maintain communities in this network, where a community is defined as a subgraph which is such that the measure of closeness within the graph is bigger than the measure of closeness between any node in the subgraph and something outside. So basically, you're in a community if you're more tightly connected to people within the community rather than people outside the community. So of course, this graph is being updated constantly, and as a result, the structure of these communities change all the time. And now a sequential algorithm for this is as follows, that you suppose you want to determine the community of one person, so you do this sort of a greedy fixed point computation that you keep on adding nodes if you find that this addition of this node increases some objective function, and you otherwise you also shed some nodes. So again, it's pretty obvious how to do this in our setting. You use an assembly to represent such a community, and then the shedding and growing of communities, the shrinking and growing of communities, is captured using the merge and the split primitives. So a few notes. So first of all, note that in the worst case, there is no parallelism here at all. The entire heap merges into one neighborhood. Second, note that the merges and the splits here are unordered. So for example, there is no real ordering between a merge that happens between, say, this and some assembly here, and the split of that assembly. So it's all completely true concurrency semantics. So what about data races? Well, so there are no data races because each assembly only updates, only modifies locally isolated objects, and merges happen only when an assembly is the recipient of the merge is not in the middle of an update. So of course, the definition of a data race is that multiple imperative computations do not attack the same object at the same time, whether for reads or writes. So what about deadlocks? So imagine a situation like this where there are two assemblies, and this assembly is trying to merge with this assembly, and this assembly is trying to merge with this assembly. So in other words, I is waiting for j, and j is waiting for I. So this is perhaps the closest to what we can define as deadlock in a situation like this. But note that merges here are unordered. So for example, if you have a situation like this, then the runtime system can really execute one of the two merges. And when that happens, the other merge, the other assembly is dead. There is no further requesting, and therefore there is no further waiting. Progress happens because a bigger assembly is formed, and that goes on to do whatever it needs to do. So the key to this is this preemptive nature of assemblies, that when an assembly is in the ready state, then it can be killed by anybody. There is no protection whatsoever. And furthermore, at the end of every update, you have to come back to this top-level ready state. So assuming that updates terminate, you are going to be able to resolve such a situation eventually. Yes?
So when J wants to merge,
right?
So it says to the system, I want to merge with the assembly that owns J.f, or the object.f, right?
Absolutely, yes.
And so if in the process, if I is splitting, so it would actually end up merging with some other assembly, some child of I.
Absolutely, absolutely.
So
absolutely.
J cannot name I specifically.
Absolutely, yeah. So that's key to this, the race freedom and deadlock freedom, yes. So of course, I said all this, but this assumes the existence of some kind of omniscient runtime system, which is going to just look at all of these things, all of these requests, and just order them and resolve them in somehow. But if you are going to write an implementation for this system in on say a multi-core machine, then there's not going to be just one scheduler that is centralized somewhere. So we'll have to talk about a more distributed runtime system, and I'm going to talk about that in a little bit. So then we'll have to reason about deadlock at a slightly lower level, and we will do so. OK, but before I go there, let me just present the language for which that runtime system is built. So this language is known as Chorus. This is simply Chorus on top of Sequential Java. So in fact, these abstractions of assembly classes can very naturally be integrated with an object-oriented language because we already have notions of object classes. So what we do is that in addition to that, we also now have these classes of assemblies. And we have these method calls from within the assembly class bodies. So we saw those guarded commands, right? So inside the updates, we can now make method calls, and these calls can now be on any of the object classes that I've defined in the sequential part of the program. And there are a few extra features that I did not show in the previous core version of the model. So we have now objects which are read-only and mutable, and these are specified as part of the types. And for example, a read-only data item can be shared ubiquitously by assemblies all over the system. And mutable objects are like what I explained earlier. OK, so in that case, the code for mesh refinement would look something like this. I'm not going to give you the details, but let's just look at this little piece here. So I have the declaration of the cavity assembly, and inside that I have this declaration of actions, and inside the actions I have calls to these methods, which are just Java methods. And similarly, we have these other assemblies, and in fact, we found that when we looked at this mesh refinement algorithm, mesh refinement application, and tried to write it in Chorus, we found that most of the code was actually just sequential Java code. We only needed to add about 15 lines of code which corresponded to Chorus. So we really could just take the sequential version of the program and then add these 15 lines of code on top of that, and we got a Chorus version of the program, which I thought was quite nice. So this is the language aspect of the problem. So what about the systems aspect of the problem? So that's what I'm going to discuss now. So one problem that you hit as soon as you try to implement something like this is that the parallelism that you express in the language is potentially huge. So in any realistic system, which perhaps has 8 cores or 16 cores, what you would need to do is that you would have to have some mechanism for mapping these hundreds of thousands of possible assemblies to the cores in the system. So how to manage this, this mapping is a thorny question. And the questions that arise here are, what are the right mapping strategies? What are the right scheduling strategies? Because a core now contains maybe tens of thousands of these assemblies, and you have to execute all of them in some order. So that raises the question, how do we schedule things? How do we balance loads, right? So this graph that we have here, that's a completely unstructured thing. So it's conceivable that after a while, some of the cores will be doing all the work. So we need some sort of load balancing strategy. And finally, what are the right data structures for maintaining the relationship, say, between the objects and their assemblies? How do we determine which assembly an object belongs to? So all of these questions need to be addressed, and this also needs to be hidden from the programmer and shoved into the body of the runtime system. So designing this runtime system is quite a challenging task. So the main lower-level abstraction that we have is known as a division. So a division is a set of assemblies that's mapped to a core. Okay, so here I see these 2 divisions. So this division contains these assemblies, and likewise. So now note that some of the merges are now actually local within divisions, because a division now contains many assemblies, right? So if one assembly within a division wants to merge with an assembly within the same division, that's just like a local operation. It's not really parallelism. However, there are these remote merges, which is that what if this assembly wants to merge with this assembly? So in that case, there needs to be an actual request sent from one division to another, and that would require some real synchronization. So these are the so this is the high-level structure of the problem. And now what we perhaps want to do is that we want to minimize the amount of synchronization that happens across divisions. We want to make most of these merges local. So how do we do that? Okay, so the main strategies here are that first, the divisions are adaptive, which is our heuristic for reducing the number of remote merges. So the idea here is as follows, that when, say, this assembly tries to merge with this assembly, you are going to migrate this assembly to this division, right? And along with that, you are also going to migrate some of the nearby assemblies to that division. So the result of that is that since there is this locality property in these applications, that typically, if you want to merge with an assembly, you're perhaps going to want to merge with some nearby assemblies, if at all, right? So that's why this heuristic of migrating some chunk of some local collection of assemblies from one division to another, that actually turns out to help quite a bit. So the second thing is the heuristic for load balancing, which is done just by a simple modification of this migration strategy, which is basically when you are doing the migration, you can also do some computation and make sure that the migration is happening from the direction of the core, which has more assemblies, to the division to a division which has fewer assemblies. So that way, you are just making sure that assemblies are always migrated from the core with more assemblies to the one with fewer assemblies. Yes?
So how does that handle the case when you have an assembly that has to merge through the whole space?
Well, so that would require a series of merges, right? So that would, in that case, there is...
At one point where it's merging from a place that's smaller than...
Right. So sooner or later, so of course, these are just heuristics. So you cannot just apply them completely blindly. So you have to also put in other heuristics. So in all these applications that we considered, it's not really that, well, with the exception of the spanning tree algorithm, it doesn't really happen that you need to merge with everything to form a big heap. So if it turns out that you're forming bigger and bigger assemblies, and you are just one division is going to have lots of stuff, and this cannot be avoided, then, well, what can you do? You'll just have to deal with that. And the third heuristic is to use the union-find data structure. And the reason for this is that these assemblies here are disjoint sets, right? So in order to maintain the relationship between objects and what assembly it belongs to, we can use a union-find data structure. So basically, when there is a merge, what we do is that we use the union part of union find. And when we want to find out what assembly an object belongs to, we use the find part of that. And so this also seems to give quite a bit of benefit. And finally, we have this token passing strategy to prevent deadlocks in this system. So as I mentioned earlier, that there is no runtime system that's completely centralized, right? That's going to just resolve all these different merge requests that are being made simultaneously. So what we do is that we have this token passing strategy, which is used in many other distributed programs as well, to handle the remote merges. So if you're going to do the local merges, these you can do at any time at your will. But as for the remote merges, you're going to need access to this global token to do that. And therefore, that introduces serialization, and that prevents deadlocks. So there is a little bit more subtlety to the deadlock freedom argument, but I think I will avoid that. I can answer that if there are questions.
There's kind of one global token, every remote.
Right. So
go through this.
Right. So what happens is that you batch all the remote requests. So for example, you have a division, right, which is executing all its assemblies in following some scheduling policy. So now you see that there is a remote merge that's being requested in some assembly. So what you do is that you batch all these requests into a queue, and then when the token comes to you, then you try to execute all of these things at one time. And this means, yes, that at one time only one person can do these sorts of remote merges. But since you are batching it, and since there are so many assemblies typically per core, it seems to work out reasonably.
Wouldn't it actually be maybe more efficient to have like master worker kind of load balancer?
What?
Kind of master worker single scheduler.
I do not know what that.
Like having single scheduler.
But you need to distribute that, right? How are you going to have it?
Parallel thing, right? It's not distributed.
Sure. But if you have these multiple cores, so where will this master scheduler run, and how are you going to find out?
That's like the global view of the whole thinking, and maybe do the load balancing much more efficiently.
Sure, but where does this master scheduler run?
Just one of the code.
But then that means that in order to do the scheduling, you are going to have to communicate, right? From that core to the core which possesses the assemblies. So you will need to basically communicate for every assembly that's going to be executed, and that will require a lot of synchronization.
When you talked about batching with this token,
Yeah.
what if we have two assemblies that are trying to merge to the same point and they batched up? These are remote merges, they're batched up, and I want to go with I and he wants to go with I. Who gets, how do you prevent like a deadly embrace type?
Right. So the reason is that when the token comes to one of the divisions, it's going to try to execute this thing, right?
Yeah.
This merge. So once that merge is executed, then that other request is voided because that assembly is dead. It's just not there any longer.
So the other one is...
It's just dead. So this is the structure of the system. So you take a program and then you pass it through the compiler front end, and then you create a Java translation, and then finally we have this runtime system, which is a layer over the Java virtual machine. So the code for this is available. Just send me an email. So this web page should be up in a few days. It's not yet up now, but if you want to look at the code, just send me an email. I'll send it to you. So let's look at some experiments. So we encoded the Delaunay refinement problem from the Lonestar benchmarks in this language. And here the data set had about 100,000 triangles. Of them, almost half of them were initially bad, and there were 1 to 8 threads. So this is what the mesh looked like after a lot of triangulation. So initially we started with a partitioning of the mesh, which was fairly nice, that it's this grid, right? And then we note that even after many thousands of retriangulations, the mesh that results still kind of looks like a grid, which means that there is a lot of locality in these computations. It's not just that the structure completely dissolves after all these operations. And so that is the property we try to exploit. So now, as for our numbers, so we have a lot of overheads actually because of the fact that we are running on top of the Java virtual machine, and we are making expensive method calls for pretty much every single thing that we are. When we try to check whether if an assembly contains a certain object or not, we have to make a method call. And it turned out that these method calls also eat up a lot of time. However, I must say that this is DSTM2, which is Maurice Hurley's software transactional library. And we are only beating the sequential version at 8 cores, but our overheads are still way better than them, at least in this application. And this is perhaps a more accurate measure of performance. So this is this is self-relative speedup, which is speedup over the sequential version of the same system. So this is an attempt to rule out some of the effects caused by these overheads. So here we noted that we are pretty much close to DSTM, but we are still perhaps a little bit better. But I would say that we are pretty much have the same curve as DSTM, which is actually interesting why these two things are very similar. So that's something to observe.
So I noticed from your graph you're relatively flat from 4 to 7 CPUs. Did you investigate what was going on there?
Yeah, so we tried to investigate, but we did not have any answer. So the problem with this Java-based system is that there is no underlying performance model. And I'm going to, in fact, show you a graph in a little bit, which is really mind-boggling. So we had absolutely no clue why this happened, but the performance started to drop just when you move from 7 threads to 8 threads. Not in our model, mind you, when you tried to use fine-grained locking. So the performance suddenly collapsed when you went from 7 threads to 8 threads. And we predict that this is because of the garbage collector, but we have no clue what exactly is happening there. So what about the number of conflicts? So we define conflicts in DSTM2 in the usual way, that how many transactions are rolled back. So we also wrote a fine-grained locking implementation, as you saw in the previous slides also. So here, a conflict meant that you are trying to build a cavity, but then you have to basically stop doing it and go back to the original state. So our fine-grained locks are not blocking locks. So basically, you try to acquire a triangle and expand your cavity. And then if you cannot, then you just jump ship and then go back to the original state and try to start again. And we found that the number of conflicts in our system is actually very, very low, which gives us hope that perhaps if we have a more efficient implementation, we would be able to get better results. Yes, please?
Have you checked the load balance?
So no, we do not have real numbers for load balancing. Primarily because the load balancing heuristic that we gave, we think that it's a very simple thing and it can be improved quite a bit, and we would like to investigate that more.
So my understanding for your load balancing is when division, if it's out of the work, try to request.
Yeah.
And synchronize waiting as a division. If the division only working on one bigger assembly,
right,
are just waiting idly until that goes down line. Okay.
Well, it's more like that you are making a request from a division which has lots of stuff to a division which has very little stuff. So now just the normal migration would bring stuff from the division which has less to the division which has more. But that doesn't seem right. So what we do is that we exploit the property that these migrations are symmetric, and we basically make the migration in the other direction.
Yeah, so it depends on number of the assembly.
Right.
But not size of the assembly.
No, the reason is that these sizes are hard to track, but one would imagine that you could improve this by having some sort of a heuristic measure of the number of objects that are there in the division currently. So as for Boruvka's algorithm, so this was the bizarre graph that I was telling you about, which is that in this fine-grained locking implementation, performance suddenly dipped when we went from 7 threads to 8 threads. And we looked at this code very, very carefully to see if there were any bugs, none that we could find. So we suspect that this is because of the garbage collector. But again, we do not really know why.
Were you running with 8 cores?
We were running with 8 cores, yes.
You had other overheads going on?
Yeah, that's possible. So the interesting thing to note here is that our self-relative speedup on this spanning tree application is actually quite decent. And the reason that the DSTM, there is no line corresponding to DSTM is that we couldn't run DSTM on this application because it's so big, DSTM just ran out of memory immediately. Okay, but here's the sad part of this application, which is that our raw speedups were rather miserable, even though our self-relative speedups were good. But again, we are hoping for a better implementation, and maybe this can be improved. But I'm not claiming that this is fundamentally because of implementation overheads. It may be that our approach has some fundamental problems, but we do not know, basically.
Graphs? Yeah.
Well,
What is the raw speedup versus self?
raw speedup is just you run the sequential version of the code, and you plot the speedup over the sequential version. Whereas in the self-relative speedup, you plot your performance versus your performance on one core or one thread. So basically the sequential version of your system, that's the baseline in this self-relative speedup. And the other one is the best sequential implementation, which is just written in just Java.
Sequential overhead is 10 times. Did I redefined 0.1?
Yeah, so exactly.
What are you doing to make it 10 times slower?
Well, so you will be surprised. So initially it was about 25 times, and then we found that if we replace these exceptions by just simple checks, like where you did not have to prepare a stack each time, then immediately it jumped from 25 times to 10 times. So now our understanding of the overheads is not that deep. It would be useful to talk to somebody who knows the details of the Java runtime system. But this is the best that we could do, at least for now. OK, and in ongoing work, I'm working with Professor Vivek Sarkar at Rice University to embed this Chorus model into Habanero Java, which is an offshoot of X10, which Vivek spearheaded the development of. So here the point is that this Habanero Java already has these abstractions for isolation. However, these are coarse-grained and static. So what we want to have is this more fine-grained adaptive construct for abstraction for isolation, which will be as you saw here. And then there are some other things that are being considered in this setting. So in particular, in the model that I showed you, the objects were either completely in the ownership of one assembly or not owned at all. However, we are considering these abstractions for fractional ownership, where multiple assemblies can own an object. However, aliasing is still very tightly controlled. And other ongoing work includes a more optimized implementation. So my student is working hard at it right as we speak. And we are also looking at a foundational process calculus for the problem. So actually, that's where we started in all of this. So I am primarily a theoretician, and our initial goal was to develop a foundational calculus for local computing in graphs. But then it became a more perhaps realistic thing. But now we still want to address this question, that what would pi calculus with merges and splits and ownership transfer look like? And we are investigating that. And finally, as somebody who's primarily interested in program verification, I'm interested in also questions about type systems for Chorus, how do we reason about type state of these assemblies, and how can you do some static analysis? So these are all questions that we want to do. And then finally, one other interesting application of Chorus seems to be in this modular robotics, where there are these self-assembling robots which are just running around in parallel, and they get together, do some stuff, and then break off again and do some other stuff. So that seems to be quite similar, at least from at a superficial level, to our assemblies and their merging and splitting. So we are looking into those applications and trying to see if we can program some of them. So for more information, you can go to this web page. I don't think this web page is up yet, but it will be in a few days. And if you want the code, once again, just ask me. And the paper is published in Uppsala this year. So if you want that, send me email too. And I'll end here then. I'll take questions.
You said you're going back into start working on like type system and static analysis.
Yeah, so we are trying to build this language and a more real implementation of this language. So we already have an implementation which you can download and use, but we want to integrate this with this Habanero. And then there are these questions of what are the types, what do types mean for this, and what kind of compiler optimizations can we do, and all those questions. So these are, yes, so I want to address these questions.
It almost sounds like almost a linear type setup.
Yes, yes. So,
but the pitfalls are always fun.
Right. Right. Yes.
So let me re-ask my question.
Okay. Good.
So this is if I wanted to use, let's say, if I want to use work stealing queue to parallelize Delaunay triangulation, right? So I would have to create a notion of a job.
Right.
A job would correspond to, I guess, triangles which are bad, or cavities that need to be triangulated.
Right.
And then push them into a queue and have threads, like, stealing jobs from the queue, right?
Right. So the question is that what kind of heuristics would you use to maintain this job stealing? So it cannot be just completely naive, right? It cannot be. So what you presumably do is that you're going to perhaps use the same kind of locality strategy, that if you are stealing a triangle, then perhaps you're going to also steal some local triangles, because that's because you will use them afterwards, right? So in some sense, you can see our division-based runtime system as an implementation of what you said, that each division has a queue which steals work from another division, which is basically about migrating these assemblies from one division to another division. And there is load balancing, but just as you are going to have load balancing in Silk. But the point is that all of those things are hidden from the programmer, because we want to also guarantee these high-level properties like race freedom and deadlock freedom and so on. Yes?
So you could compile your language to Silk, for instance, with work stealing queue.
Yes, that's actually a thought that I did not have, but yes, that seems like a possibility, yes. I mean, okay, so I would be hesitant to say yes completely, and the reason is that these questions like deadlock freedom, there we have to do some special things to to ensure that. So I do not know if we just do a naive translation into Silk, we will get all those properties automatically. So that will require some thought.
Okay, but we can talk about it.
Sure. Yes?
So how do you make sure there's no aliasing on a single ownership?
Oh, because there is there are no references being transferred, right? The only way you do any kind of passing of objects from one assembly to another is via this merge, right? Or split. So when you do a merge, you are just giving the entire region to another assembly. So you are not.
So basically, but you're like on the language level, you are passing all the loads and stores, and you see that they're going to your local part of the heap.
Yes, that is right. That is right. Yeah. Yeah. So that's where the find operation comes in.
So this is probably the major bottleneck, right? Of the every read and write, you need to intercept and check that it goes.
Right. So not every one of them.
This is the reason for this 10% slowdown, right?
I agree that that is perhaps. Yeah, so I agree that is perhaps the biggest bottleneck. But I think, so one clarification though is that we do not need to monitor every single writes. So really we can store some notion of a boundary of these objects. So you can do some optimizations which will guarantee that certain accesses are guaranteed to be local. But sometimes you're not sure, and then yes, you will have to do this sort of check.
It's like the same with transactional memory, right?
So one difference, though, is that you are doing this only at a completely local level, right? So in case of the transactional memory, if you have at least an implementation which is global, your conflict detection routine is going to have to go through the entire memory. Whereas here, this sort of check that whether you're going outside or whether you're staying inside, that's something that you are doing using that find operation in union find, right? And it's also a local thing that, if this, as you saw in that mesh refinement example, an assembly contains what? Maybe 10 triangles. So it's really about checking these 9 or 10 edges that go out of an assembly and try to see if.
And it depends on the size of the.
Absolutely. So this is.
Of the heap part of this assembly. So.
Sure. So, but what I'm saying is that the property that we are trying to exploit is that there is a lot of parallelism at a low level, at a fine-grained level. And that's the property we are trying to exploit. So in cases when there is no such parallelism, then yes, it will just reduce to doing these sorts of global checks.
Understand like the overhead of these checks.
Sure.
The single ownership. They're kind of essentially the same as with transactional memory. I mean, you can have better, more efficient implementation maybe with more efficient data structures.
No. But the basic point I want to make is that the only difference between that sort of checking that goes on in transactional memory and here is just that we are using this local property that we are operating on local regions. So if you said that this was these assemblies contain the entire heap, so in that case, yes, there is no difference at all in terms of overheads.
With multiple transactions, you can access something outside of transactions, so you need to monitor, right?
No, but remember that in transactions, there is no annotation of this is the region that this transaction belongs to. So transactions are referred to atomicity of control in some sense. And the data is really just one global blob, and you can just go do whatever you want to do with it. So,
you read-write sets yourself.
The what?
You maintain the read and write sets yourself.
Sure, but if you have heap allocated data structures and if you have field expressions, then you will have to basically do either some kind of analysis, some kind of shape analysis to see how far you can go, or you'll have to do it dynamically by doing a check. So here, all we are exploiting is the locality property. That in these applications, the parallel computations are restricted to these local regions in the heap, and that's what we are exploiting here.
Any other questions? Question. So
Yeah.
can you comment something about the ease of programming with respect to say, fine-grained locking or transactional memory?
Well, so transactional memory is easy to program in, but fine-grained locking is pretty horrible. Even in these applications which are not that complicated, just trying to make sure that there are no deadlocks and no aliases are going from here to there. So that's a huge pain. So I think that in terms of ease of programming, as you saw, that application took only 10 lines of extra code over the sequential version. So I think that it seems very natural, at least for these classes of applications.
10 lines, 90%.
The what?
10 lines, 90%.
10 line is.
Well, you only get 10% of the performance with
Oh,
10
sure,
li-
sure,
with
sure.
10 extra
Sure,
lines
sure.
of code.
Yeah, that's true. No, but there I would point you to DSTM.
Okay, so let's thank the speaker again.